you. Thanks for the invitation to this. It's good to be giving talks in person after a while. So I'm going to talk about the matrix completion problem, which is basically a problem that has been looked at by statisticians and people in machine learning. And there is something to say in terms of graph limits, graph fonts. So maybe, and there are some open questions, so maybe something good will come out of this talk. I haven't given a talk on this before. It's a couple of years old. So the problem of reconstructing a large low-rank matrix from a subset of revealed entries, this has, there are literally now thousands of papers on this. So you have a large matrix which is assumed to be of low rank, and only a subset of entries are revealed, and you have to guess the rest. So it comes from this problem of recommender systems where people give ratings, and low rank is sort of natural assumption. Now it's if you think about it, it's just a problem in linear algebra. But if you look at the classical linear algebra literature, the matrix completion is restricted to matrices with special structures, such as positive definite matrices. If you just assume low rank, then most of the modern literature assumes that a certain fraction of entries are missing uniformly at random. Okay? And so it's there's a 40-minute talk, so I'm not going to talk about the review so much. So I'll give you the reference to my paper, and you can look at a more extended review. And so this assumption, missing uniformly at random, is not realistic, but you can prove very nice theorems with this. And there are only a small number of papers which work with deterministic missing patterns, or missing patterns that depend on the matrix, so not uniformly at random. So this was the primary motivation of the work. That is, if you just consider the linear algebra problem, if you have a large matrix, you assume it's low rank, and a certain pattern of entries is missing, when can you approximately fill in the matrix? If you don't want to make any assumptions about this missing, what is missing or how is it related to the data, any model on the missing pattern. So I'll give you a complete characterization, I should say asymptotic characterization of missing patterns that allow approximate completion of large low-rank matrices. And this is from this paper from 2 years ago. And this characterization will be in the language of graph limit theory. Okay, so this will tell you exactly what kind of missing patterns allow completion of large low-rank matrices. So first of all, just to begin, it's important to note that not all patterns of revealed entries allow low-rank matrix completion. Even if you make the assumption of low rank, and even if you just want completion in an approximate sense, you don't want the exact matrix back, but only approximately. And even if a substantial fraction of entries are revealed, and there's a very simple example. So for example, if you have an n by n matrix and you only reveal the top n over 2 rows, then there is no way you can complete the bottom n over 2 rows, even if you assume the matrix is low rank. That's just impossible to do. So this cannot be completed means that there are multiple very different ways to complete, which are all low rank. So this is not a missing pattern that you can handle in any reasonable way. Okay. So any particular completion cannot be a reliable estimate of the matrix if this is the pattern of missing entries. Now, this example suggests that the set of revealed entries has to be in some sense dense in the set of all entries. So if there's a large, square, yeah.
I have a question. When you say complete a matrix, is it with some criteria you want to complete it? Or?
Yeah, so low rank. So assume it's low rank. Okay, assume it's low rank. But even under the assumption, even if you assume it has rank 1, you cannot complete this matrix if this is the pattern of missing entries.
That's the criteria you want to maintain?
Yeah. So that's the general criterion that people have assumed in the literature. So this suggests that the set of revealed entries has to be dense in the set of all entries. So if there's a large, empty box where everything is missing, then obviously even under low rank, you cannot complete it. Okay. However, one has to be cautious. So consider a second counterexample. Suppose n is even and consider an n by n matrix whose igth entry is revealed if and only if I and j have the same parity, if both even or both odd. So this is a kind of like a checkerboard pattern. So these are the revealed entries, the shaded ones. So this will argue that the recovery is not possible even if the rank of the matrix is as small as 3. Okay, and this is a pretty dense pattern of entries. So what you do is, again, something very simple. You just permute rows and columns so that the even numbered rows and columns are numbered from 1 to n over 2, and the odd numbered rows and columns are numbered from n over 2 plus 1 to n. And with this permutation, the missing pattern just becomes this. So although this looks dense here, after permuting rows and columns, you get this very large missing blocks. Okay. So again, this becomes impossible to estimate even if you assume low rank. Okay. So clearly this cannot be recovered reliably even if the rank is as small as 3. Questions? Okay. So the problem with the second example is that the rows and columns could be relabeled so that the pattern of revealed entries again is no longer dense. Okay, so that's a problem. So this suggests that for recoverability of low rank matrices, it is necessary that the pattern of revealed entries remains dense under any relabeling of rows and columns. So however you relabel rows and columns, the missing entries should always look dense in the matrix. That must be a necessary condition, because if that's not there, then obviously you cannot complete the matrix. It turns out that this condition is also sufficient, but that's a little difficult to express. And that's one of the open questions, how to have a finite sample version of this. So this is the first main theorem. The precise statement I give in the language of graph limit theory. So only as a limiting statement I can give this. So what do I mean by saying that under any permutation of rows and columns, the pattern of missing entries remains dense? And so it would be very nice to have a finite n version of that, but I don't have. I have a limiting version of that, and I'll display that. And so it turns out to be a necessary and sufficient condition for recoverability of low rank matrices. And the second result is that, well, this is a necessary and sufficient condition, but how do you recover the matrix? What's an algorithm? It turns out that a nuclear norm minimization algorithm of Candace and Recht, this succeeds in approximately recovering the full matrix whenever this condition holds. So a small modification. So you basically have to impose a supremum norm constraint as an additional convex constraint. And then it turns out that this is always able to approximately recover the matrix whenever this condition holds. So not only is this condition that I'm going to present necessary and sufficient for missing patterns which allow the matrix to be recovered approximately, there is also a simple algorithm for doing it. Okay, so let me give the precise statements. First, some matrix norms. Let A be an m by n matrix, so all real entries. We define the average Frobenius norm as follows. So you take the average value of the sum of the squares of the matrix entries and take the square root. So this represents the sort of in some sense, the average size of a matrix entry. If these are the non-zero singular values, the nuclear norm is defined as the sum of the singular values. The L infinity norm is just the maximum matrix entry. And finally, the cut norm, I define it in the following way. You take the maximum of absolute value x transposed ay, where x and y are vectors with L infinity norm bounded by 1.
Should you have absolute values for the singular values?
Well, I'm assuming singular values are defined as non-negative, so like the square roots, yeah. So that's, yeah. So instead of eigenvalues, you have singular values. So, and the cut norm is a maximum of absolute x transposed ay, where x and y are vectors of L infinity norm bounded by 1, and I divide by 1 over mn for a certain normalization. Well, this will not be important. So these are various matrix norms. And this one in particular will be useful in our statements. It is a measure of the average size of the matrix entry. So if this is small, you know that the matrix has small elements. Another thing that I need to define is the cut distance between two matrices. So let Sn be the group of all permutations of 1 up to n. And for any two permutations pi and tau, and the matrix A, let A pi tau be the matrix whose ijth entry is A pi I tau j. So you apply pi and tau to permute the rows and columns, and you permute this matrix. And then the cut distance between two m by n matrices A and B is, you take the minimum over all permutations of rows and columns of A and subtract B from that and take the cut norm. So basically you're permuting rows and columns to make the matrices as close to each other as possible in the cut norm. So that's the cut distance. So this is all from graph limit theory. Any questions about the matrix norms? Okay, so next we'll say a matrix is a binary matrix if its entries are 0 or 1. And we'll use binary matrices to denote the locations of revealed entries in matrix completion problems. So where are the missing entries? So those are zeros, and available entries are 1. Hadamard product. So sorry about so much terminology, but that's all I need. The minimum I need. So if A and B are two m by n matrices, the Hadamard product is just entry-wise product. So it's another m by n matrix whose And the way I use the Hadamard product is that if A is a matrix which is partially revealed and P is a binary matrix indicating the locations of the revealed entries, then the Hadamard product of A and P is a matrix whose entries are equal to the entries of A whenever they're revealed and 0 elsewhere. Okay, so this is a simple notation that makes it easy to write down things. Okay, so let me now give you the notion of when I say certain patterns allow you to recover entries. So let me make that precise. So certain patterns of revealed entries may not suffice for approximately recovering the full matrix, whereas other patterns may suffice. So this makes some sense intuitively, but to give a precise definition, we take this approach. So what we say is that approximate recoverability means that if two low-rank matrices are approximately equal on the revealed entries, they should also be approximately equal everywhere. Okay. So again, I'll make this completely precise, but this is what I mean by saying that you have recoverability, approximate recoverability, where I mean that if you have two low-rank matrices which are approximately equal on the revealed entries, then they should also be approximately equal everywhere. And this is not true in the two counterexamples I showed. So you can have two low-rank matrices which are approximately equal on all the revealed entries, but they're very different in the unrevealed entries. Yeah.
Should the have equal rank?
No, just just low rank, not necessarily equal rank. So to make this fully precise and to capture all possibilities, I need a limiting statement. Okay, so if I have a finite statement, I will have to restrict myself to some smaller class, something. So I don't want to do that. So that's why I need a limiting statement. So here is the definition. It's a little long. So let PK be a sequence of binary matrices possible in different dimensions. Typically, we'll take increasing dimensions. We'll say that this sequence admits stable recovery of low-rank matrices if it has the following property. Take any two sequences of matrices AK and BK, where for each K, AK and BK have the same dimensions as PK. And suppose the ranks and the L infinity norms of these sequences of matrices are uniformly bounded. Okay, so you have two sequences of matrices with uniformly bounded ranks, uniformly bounded L infinity norms. Then it should be true that for any epsilon, there is some delta, so that if the average size of the revealed entries in the two matrices differ on average by less than delta in a limiting sense, then the average size, average difference of the entries everywhere should be less than epsilon. Okay, so if they are small on the revealed entries, if the difference between the two matrices is small on the revealed entries, and the matrices have ranks and L infinity norms uniformly bounded, then the matrices themselves should be close to each other. This is the limiting statement which captures all possibilities without speaking of any rates of convergence. If you give a finite definition, maybe there is some way, but I thought about it in terms of just fixed matrices, and there is no sensible, doesn't seem to be a sensible way to capture this idea. So this seemed to me to be the only way to do this, but I may be wrong. So any questions about this definition?
The dimensions are changing, you said, for the KPK, right?
Yeah.
They're all some fixed MNN.
So each PK has some dimension, call it MK cross NK. And MK and NK are typically going to infinity, but I don't need that in definition. But in examples, I'll have. Yes. No, so I don't want them to be equal on the revealed entries. I want them to be approximately equal on the revealed entries.
Okay, and can you comment on that, or is this
so that's an important thing. So if they're exactly equal on the revealed entries, it's so this is I have a remark about that. So this is why I say stable recovery. So if you assume that they're exactly equal on revealed entries, the situation is a bit different than when you say that they're approximately equal. So stability means that even if they're approximately equal, you can deduce that they're approximately equal everywhere. You don't need exact equality.
That is, you allow this sequence of matrices growing, and nothing is dependent on the dimension of matrices.
So
this means that if you take this limit and the matrices are growing, and you have this bound on the Frobenius norm, it means that then each entry will be very close, right?
No, so this is bound on the average Frobenius norm. So F bar, as I wrote down here.
It's normalized by the dimension?
Yeah, it's normalized by the number of entries. So the average Frobenius norm denotes the approximate average size of the,
okay,
of the entries. Yeah, not the Frobenius norm.
Questions?
So we'll say that this sequence of binary matrices admits stable recovery of low-rank matrices. If this is true for any two sequences of matrices with uniformly bounded ranks and infinity norms, you can have this. Okay. So to show that it does not admit stable recovery, you just have to produce one counterexample. And so this is the remark that I said. The word stable is added to definition to emphasize that we need only approximate equality of the revealed entries rather than exact equality. And the two examples discussed earlier, you can very easily produce counterexamples to show that they do not admit stable recovery. Okay, so now you can make a precise sense of what I just said earlier, that this will not allow you to recover. You have, for each n, you have a missing pattern, and then you can produce a sequence of low-rank matrices where they are equal. You can actually get exactly equal on the revealed entries, but the average difference, if you consider all entries, that is not going to 0. Okay, so to verify that a sequence admits stable recovery of low-rank matrices, we need to verify that the stated condition holds for all sequences of matrices AK and BK. But it would be much more desirable to have an equivalent criterion in terms of some intrinsic property of this sequence itself, okay, instead of verifying it for all AK and BK. So this is what we are aiming for. And our first main result gives such a criterion. To state this result, we need the language of graph limit theory. So I'll just state a few things, and many of you are familiar with that. So in graph limit theory, a graphon is a Borel measurable function from the unit square into 0, 1, which is symmetric in its arguments. And you are dealing with matrices that need not be symmetric, so we need to generalize the definition by dropping the symmetric condition. So we define an asymmetric graphon as a Borel measurable function from the unit square into 0, 1 without the condition of symmetry. Okay, so just that one. Now, if W is an asymmetric graphon and M and N are two positive integers, we define the M by N discretization of W to be the M by N matrix whose ijth entry is the average value of W in this rectangle. So you take the unit square, you divide into M by N little pieces, and on each piece you take the average value of W, and then you define a matrix. And if A is an M by N matrix and W is an asymmetric graphon, we define the cut distance between A and W to be the cut distance between the matrix A and its discretization of W. Okay. So this is just, I just define this like this, and there can be other ways of defining this, but I'm just defining it in this manner. We'll say that the sequence converges to an asymmetric graphon W, a sequence of matrices, if this cut distance goes to 0 as k goes to infinity. So a sequence of matrices will converge to an asymmetric graphon if this happens. And note that the same sequence may converge to many different limits. And in graph limit theory, typically all these different limits are considered to be equivalent by defining an equivalence relation of space of graphons. And we can do the same for asymmetric graphons, but we don't need to worry about that right now. We can think of this as, you organize the matrix, permute the rows and columns of the matrix in such a way that it converges to some reasonable limit. So we'll use asymmetric graphons to represent limits of binary matrices. And not every sequence of binary matrices will have a limit, but the following result, which is a standard thing in graph limit theory, but I didn't see it written down for asymmetric things. Maybe there is somewhere. So any sequence of binary matrices with dimensions tending to infinity has a subsequence that converges to an asymmetric graphon. And this is the asymmetric analog of a compactness, of a fundamental compactness theorem in graph limit theory due to Lopez and Szegedy. So you can always have subsequential limits. Given any sequence of binary matrices, you can have subsequences converging to asymmetric graphon, and any subsequence will have a further subsequence and so on. So the reason I state this result is that we want to give a necessary and sufficient condition for a sequence of binary matrices to admit stable recovery of low rank matrices. This is our goal. Yeah. So you need
both the rows and columns to go to infinity. When you say dimensions go to infinity.
Yeah, both rows and columns going to infinity. So we want to give a necessary and sufficient condition for a sequence of binary matrices to admit stable recovery of low rank matrices. And because of the compactness theorem, it suffices to only consider convergent sequences, because any sequence of binary matrices will have convergent sequences, subsequences, and so we can state the theorem just in terms of convergent sequences of binary matrices. So here is the first main result: a sequence of binary matrices with dimensions tending to infinity and converging to an asymmetric graphon W admits stable recovery of low rank matrices if and only if W is non-zero almost everywhere with respect to the Lebesgue measure. So this is what it means when I say the finite statement that you have a missing pattern where any permutation of rows and columns will keep it dense. You can never get a large block of empty entries. And the limiting version of that is that these matrices are converging to a limiting graphon, which is non-zero almost everywhere. And graphons, as I said, are equivalent under measurable bijections of the two coordinates. And this condition being non-zero almost everywhere is preserved under that. So it's a characteristic of the equivalence classes. Okay. So this is the necessary and sufficient condition.
So you're allowing for low rank matrices, but you're not allowing for sparse matrices, right?
Yeah, so I'll give a comment. I'll give a
zero.
comment about that. So what is going on with sparse matrices?
Non-zero almost everywhere is sort of saying it's very dense, right? I mean, you have no open spaces really.
Yeah, no open spaces.
The condition of matrix P on the matrix of sample.
Of what?
This theorem is the condition for sequence of matrix PK, the matrix of observation pattern, not the matrix that we want to recover.
No. So this is just a condition on the missing patterns. So if a sequence of missing patterns satisfies this condition, then and then you have two sequences of low rank, any two sequences of low rank matrices. So low rank meaning uniformly bounded rank, and I'm assuming uniformly bounded L infinity norm. Two sequences of such matrices, which are approximately equal on the revealed entries of this sequence of binary matrices, then they must also be approximately equal everywhere.
In a certain sense, this is saying that the revealing should be independent of the matrix, right?
Yeah, yeah, and that
You don't
that
allow for these dependencies.
Yeah, so this is so you can use it. So I have used it with one of my students. I'll give a remark about that later on, where the probability of an entry being missing depends on the entry, and you can have all kinds of complicated things. So you can have very complicated missing patterns as long as you can prove that the limiting graphon is non-zero almost everywhere. You are done. So the case of uniformly missing at random is a very simple case where the limiting graphon is just a constant. And so it holds in that case, but it does not need to be that. It can be something extremely complicated that depends on the matrix and depends on the data. Yeah.
I don't have a really good intuition for these asymmetric graphons. Is that equivalent that some version of subgraph counts has to be non-zero for every subgraph?
So I could not do it with the subgraph approach. So the way I prove the compactness theorem is by adapting the spectral proof, using the spectrum. So using singular values instead of eigenvalues. So I don't know how it translates in terms of subgraph counts.
It should be bipartite graph count.
I guess there may be some way of doing it with bipartite graphs, but
But the question is there some way to say that that this W being non-zero, how do we relate that to the subgraph counts?
Yeah, I don't know that. So I visualize this as saying that no matter how you permute the zeros and ones, the ones always zero. But you cannot somehow come up with some blank region. That's how I interpret that.
So of course, this depends on the measuring things with the Frobenius, average Frobenius norm.
Yeah.
Do you have a sense of what happens if and are there other meaningful norms that one should consider, and how does that change?
Yeah, one can consider. I would think that any norm which sort of measures the average size of the entries should give the same result, but something like the spectral norm will be different. So that would be.
Thank you. And just to clarify, is there any assumption that the dimensions are going to infinity or anything like that, or?
Yeah. So with dimensions.
Sorry. Yeah.
Seems to be it for the moment.
Okay.
Please proceed. Oh.
Okay, so to understand this result, first consider the case of entries missing uniformly at random, as I said. So suppose that each entry is revealed with probability p independently of each other. Then the corresponding sequence of binary matrices converges to the graphon that is identically equal to p. And if this p is positive, the theorem tells us that the sequence of these patterns admits a stable recovery of low rank matrices, which is a well-known result. On the other hand, consider the example where only the top half of the rows are revealed. This will converge to the graphon that is 1 on this rectangle 0 half cross 0 1 and 0 in half 1 cross 0 1. And this is there's a positive region where it's 0, so this does not admit stable recovery of low rank matrices. So here is the paradox that some of you have already pointed out, that one may be puzzled by the fact that this theorem implies a stable recovery is impossible if the set of revealed entries is sparse, because the limiting graphon is identically 0, whereas there are many existing results about recoverability of low rank matrices from a sparse set of revealed entries. Okay? So the issue is that we are not assuming randomness and at the same time demanding that the recovery is stable. Okay, that is the reason. So what happens is that suppose you have two low rank matrices and most entries are the same for the two matrices, but the entries that differ are only the ones that are revealed. Okay, so since you are not assuming that the pattern of revealed entries is uniformly at random, we are not assuming anything about it. It may be that only the bad places are revealed, where the matrices are different. And then there is no way to tell that the matrices are mostly the same. Okay, so if you don't assume randomness, you run into this problem that you can have, and only a sparse set of entries are revealed. You can have this problem that the matrices are different just on that sparse set. Okay. And that's why the stable recovery is impossible from a small set of revealed entries if there is no assumption of randomness. So if you want recovery of low rank matrices from a sparse set of entries, you have to, maybe uniformly at random is not necessary, but I would think that some assumption will be necessary. You cannot just have an arbitrary deterministic thing, because you can't just reveal a small set of bad entries. Yeah.
So instead of making randomness assumption, if we have assumption like finite rank and there is a gap in the spectrum of the missingness, so under those conditions, can one prove some results?
Yeah, I think there is some literature on expander type, missing patterns.
Expander missing.
Yeah, so there is some literature. So, it's in the paper. Okay, so the next thing is how to recover the matrix. So the theorem gives an intrinsic characterization of recoverability in terms of the locations of the revealed entries. However, it does not tell us how to actually recover the matrix when when recovery is possible. So suppose you know that that recovery is possible. How do you recover the matrix? So fortunately, it turns out this is doable by a small modification of an algorithm that is already used in practice. This is the algorithm of Candace and Recht of a partially revealed entries is the matrix with minimum nuclear norm among all matrices that agree with A at the revealed entry. So suppose you have a matrix which is revealed only partially. Then you look at all matrices which agree with this matrix at the revealed entries, and you take the one that minimizes the nuclear norm, because that's the Candace-Recht algorithm, and it works very well for missing uniformly at random, and it even works well if missing uniformly at random but only a small set of sparse set of entries. So this is a modification. So let A be a matrix whose entries are partially revealed, and suppose we have some additional information. We know that the L infinity norm is bounded by L for some known constant L, and this is not unrealistic. In most practical problems, we'll know some bound on the entries. We define the modified estimator of A as a matrix that minimizes nuclear norm among all B that agree with A at the revealed entries and satisfies this L infinity bound on the matrix entries. So these are both convex constraints, so it's a convex problem. So it should actually, I think, an option already exists in the R code. If you want to have the entries bounded. So you just find a matrix which agrees with your given matrix at the revealed entries and has the same L infinity norm upper bound and minimizes the nuclear norm among all such matrices. So this is your estimator. So as I said, the assumption of a known upper bound on the L infinity norm is not unrealistic. Usually such upper bounds are known. And the modified estimator is a solution of a convex optimization problem, just like the original estimator. And so, and I think the code exists. So because my student was able to do it. So the dimensions are not too large. So the following theorem, this is the second result of this talk, shows that this modified Candace-Recht algorithm is able to approximately recover the full matrix whenever the pattern of revealed entries allows stable recovery. So this is the theorem. Let PK be a sequence of binary matrices with dimensions tending to infinity that admit stable recovery of low rank matrices. So this already, you are assuming that this is a sequence which admits stable recovery of low rank matrices. And we know a criterion for that, stated earlier. Let AK be a sequence of matrices so that for each K, AK has the same dimensions as PK. Suppose that rank and L infinity norm are uniformly bounded and an upper bound on the L infinity norm is known. Let A hat K be the modified Candace-Recht estimate of AK when the locations of the revealed entries are given by PK. Okay. So then the average Frobenius norm tends to 0. So this Candace-Recht.
Why do you insist on this upper bound being known?
Well, because that's in the modified algorithm that we have to use the upper bound to get the estimate. So I'm I'm given a matrix with partially revealed entries, and looking at all matrices which agree with the given matrix at the revealed entries, and satisfies this L infinity upper bound, and then minimize nuclear norm among all such matrices. So it's in the algorithm. So otherwise, you can have some issues where you can have small L infinity norm, but one entry can become very large, and then it destroys this average Frobenius norm. So that kind of issue can come up.
So does the upper bound L appear in the air when something converges to zero? Does that depend?
So there is no error. There is, it's just limiting statement.
Yeah, but let's look at the pre-limit. Does that depend on L?
Well, it's from graph limit theory. So that's,
okay,
through the
pretty
power
abstract.
of 2. Yeah.
Okay,
So,
good.
So it's not something that can be said aloud.
When you use this nuclear norm, you have to still minimize over all permutations, right? Or not?
No. So you are just given a matrix with some entries are revealed, some are hidden, there are question marks. So you just look at all matrices which agree with your given matrix at the revealed entries, and any arbitrary values at the missing entries, and then you with this constraint that additional constraint that the entries are bounded by this L, and then you minimize nuclear norm among all such, and that's it. That's all. You don't have to do all permutations or anything.
I see. So but you also have to. What about the rank?
No, you don't have to worry about the rank.
So you will not necessarily get a low rank matrix.
No,
out.
not necessarily. You'll not necessarily get a low rank matrix. Okay, so this is the theorem. Any other questions? Okay, and here's an application. So, I don't know enough programming to do this, but then in a follow-up work, so consider a setting where the probability that an entry is missing is an unknown function of the value of the entry. So that's the simplest kind of complexity above uniformly at random, maybe one can imagine. And so we wrote this follow-up paper with my student Sourav Bhattacharya, where under a Lipschitz assumption on this unknown function, we could show that the modified estimator works. The best thing about this paper perhaps is that Sourav was able to actually carry this out on the computer, and it works really well. So if you have some function and the probability of missingness is a function of the matrix entries, we have pictures where the function is very accurately recovered. So the results presented here were key to the proof in this paper also. Okay, so there's some open problems. The definition of stable recovery entails that the revealed entries are only approximately equal to the corresponding entries of the unknown matrix. So if you drop this condition, assume the revealed entries are exactly equal to the true entries, how should the theory be modified? Okay, so do you get something different? Do you get some additional? Because this is better that if we exactly know the revealed entries. So maybe we can get something more. I don't know. This is a thing that has been bugging me for a long time, and this is actually the original thing that Sourav and I wanted to do, but we couldn't. Developing non-asymptotic versions of this theorem is extremely desirable. So it's not quite clear what should be the proper non-asymptotic statements that one can aspire to prove. One measure of this thing is that suppose you have a pattern of missing entries, then you look at the largest submatrix that's completely missing. So largest maybe number of entries in terms of number of entries, and can one use that as a measure and get a finite sample error bound, just in terms of that largest completely missing submatrix. Okay, so that would be extremely nice to have, and I don't know how to do that.
So if you put that in the framework of graph limit theory, at least for symmetric version, there is, except for this compactness argument about the existence of a convergent subsequence, but everything else in the theory of graph limits is done explicitly. I mean, your errors may be e to the 1 over epsilon squared or something like that. But
but the problem is that.
So why couldn't you? So I wouldn't look at how many entries are 0. I would look at the distance from the 0 matrix in the cut metric.
Yeah.
And if that is bounded uniformly in N from below, that's probably as good as. Then you could argue if you had a limit, the subsequential limit can't be 0, otherwise you would have a contradiction. So why can't you just plug in, say, okay, I assume this is bounded below some epsilon, and now you do your whole theory. I mean, it's 200-page papers you have to go through, and redo them for the non-symmetric case. But I don't quite see where you, unless you're using in more places compactness where you sort of just have no control of the errors. But if you put the Semeredi lemmas and stuff, you should get explicit errors, no?
Yeah, I should get, but the problem is that in this convergence of this PK, the missing pattern to this limiting graphon, I have to assume something about this rate of convergence. So that's the problem that I didn't quite know what to do. How close is your missing pattern entry, missing pattern matrix to the limiting graphon? I mean, it's the same reason why as far as I know, there is no finite sample version of the Aldous-Hoover theorem. So the Aldous-Hoover theorem will tell you that there is if you have a row column exchangeable infinite matrix, there is a function f so that the xij is f of ui, uj, uij. But if you actually want to get your hands on this f, so unlike Definitive's theorem, there is no finite version of Aldous-Hoover theorem as far as I know, and it's the same reason that that you need to assume something about the rate of convergence. Otherwise, yeah. So I don't know. I couldn't do it. That's all I can say.
Need convergence. I mean, as you said, you would have converged with subsequences, but your statement.
So why would you need convergence if your pattern matrix is just, let's say, uniformly bounded away from 0 in the cut norm? Okay. Well, if you want to assume a subsequence and convergence, but why do you even need it? I mean, your theorem doesn't in the end have it, right? You just need that this cut metric is sort of bounded away from 0. Then any subsequence would converge to a non-zero matrix. But in your theorem, you never, in the end, you always said without loss of generality, but you don't have to assume convergence, right? So wouldn't your statement just hold without the convergent assumption?
So that's also interesting. So there are two theorems. In the first theorem, I am assuming that the binary matrix is converging to an asymmetric graphon, and then I say that this sequence of binary matrices admits stable recovery if and only if W is non-zero almost everywhere. So that's in the first theorem. But
so, as you said, your theorem has immediate corollary that it holds. So assume I had this matrix.
So assume I have this matrix of 0 ones. It's bounded away in the cut metric from 0. Okay. So now I claim your theorem holds. Why? Well, I choose a subsequence. On the subsequence, it will converge. That will converge to a non-zero graphon. So on that subsequence, it holds. Now you go to another subsequence, do the same thing. And so you know by your theorem and using subsequences, your theorem actually holds if your sequence of pattern matrices is bounded away from 0 in the cut norm.
But the thing is, I'm not assuming that W is away from 0 in the cut norm. I'm assuming that W is non-zero almost everywhere. So it cannot.
But that's the same.
No, cannot even have a small region where it's 0. It cannot even have any set of yeah. So it's
So so this comes sort of back to my previous question, right? Is there some more combinatoric way of characterizing this sort of, as you call it, density assumption?
That's the open question. Okay.
All right.
So this is the open question. So this condition that this revealed entries, this matrix is close to a graphon which is non-zero almost everywhere. How can you quantify that? That's the thing that I don't know how to do. I'll just do 3 more small open problems. Developing a version of the theory that works for sparsely revealed matrices. You have to make some additional assumptions for sparsely revealed matrices. So one thing that was not clear to me is if this algorithm indeed needs to be modified. I think the L-infinity bound is important, but I couldn't prove it. It would be nice if the original version is good enough, but it's not hard to code even with this additional constraint, so not a big deal. The other problem is that this algorithm is rather slow for very large matrices. It's a convex optimization problem. If you have huge matrix, then it's not a good thing to use. Is there a faster algorithm, maybe using some spectrum or something else, which can take its place and give the same result, that it works whenever the recovery is possible? Okay, thank you.
Thank you very much for this beautiful talk. There has already been a lot of discussion, but we can continue now. Olga is first.
Thank you. Thank you very much for a nice talk. Actually, I'm a little bit puzzled about the algorithm. So condensed-Gauss, condensed-Recht algorithm is about the exact recovery. Yeah. So this is why they're asking matrix equal to observed entries. Yeah. And then in your definition, you have approximate recovery, right? Yeah. And then the algorithm is called matrix lasso, exactly the same constraint on the subnorm, where minimize the least squares plus the nuclear norm. Do you need really the exact equality of the entries, or you do need this relaxed form of estimator?
So in the algorithm that I stated, I am I'm considering all matrices which exactly fit the revealed entries, but the theorem tells you that the matrix will be approximately recovered even if the revealed entries are slightly noisy.
But I'm asking about the algorithm. So the condensed algorithm, so you like 2 versions of this algorithm. One's from the original paper, where they're looking for exact recovery, and then they say, so my matrix equal to what I observe. And then there is this other version, you take the least squares, so you're looking for the best fit, penalized by the nuclear norm.
Yeah, so, no, I'm looking at the original version. So here is so I'm just taking exactly revealed. So I'm not taking the noisy version. So the reason is that even if there is noise, this I'm assuming that noise is extremely small. So I have approximately the revealed entries are approximately the same as the original entries. So yeah. No, I didn't understand. So
in the definition of recovery, you use the normalized norms more equivalent data.
Yeah.
Means that you have enough noise to change it, right? Of order like bounded noise.
Yeah, bounded noise, but basically this delta and epsilon are small. That's the thing. So the epsilon will depend on delta. If you take delta small, epsilon will be small. In particular, if delta is 0, then epsilon will also be 0. So epsilon will depend on delta. So it's a continuity kind of result.
So coming to the question of spectral algorithms at the end of your talk. So if I am trying to apply, say, universal singular value thresholding algorithm, so what would be like the most general condition would you expect under which the
so universal singular value thresholding unfortunately will not work. So in my paper at home, we have proposed a modified version of that, which will work under this particular setting where the matrix entries are functions of universal singular value in universal singular value thresholding, it's important that the missing pattern is the pattern of missing entries is uniform at random. If it's non-uniform, you have to modify the algorithm. The good thing about the Candace-Recht algorithm is that, as I found while working on this paper, that it works even if you have completely non-uniform missing patterns. And so I think it's more generally true. So what I presented here is one version of that, but it's probably true in much greater generality that the Candace-Recht in nuclear norm minimization just works for completely non-uniform.
Thank you very much.
Okay.
Beautiful talk. There's coffee and tea now, and we reconvene at